today we're talking about how much performance you can get out of JavaScript and, of course, how to get that performance out of JavaScript. So first of all, just a few words about myself so that you get the picture of what I'm talking about. Things I worked on. I worked on the Mono just-in-time compiler. It's a project about doing .NET as free software, and I did this for about 6 years. And worked on the Unity game engine, porting Mono on the Xbox and things like that. So again, virtual machine work. And I worked in the V8 team in Google, which is where I learned how actually JavaScript performance works for about 1.5 years. Now I am a stack developer at Hyperfair, where we do virtual reality on the web, which is cool, but not really related to this. Anyway, does JavaScript performance matter? And well, of course it does. So let's ask another question. Does JavaScript performance matter to you? And of course, it depends on what you're doing. Because if you're doing simple things, just IO bound, it doesn't really matter to you. But let's ask a different question. Should I know how to write high-performance JavaScript? And then again, it depends what you're doing, but we are getting there. And the idea is, should I know the potential of JavaScript performance? And now, this is the correct questions. I will say, why should this be the correct question? The point is that if you don't know how much performance you can get, you cannot imagine new things because you don't know the potential. So you don't know if new things are feasible. For instance, would you imagine adding a neural network working in real time inside a web app? Would you ever dare thinking about it, or doing that, or attempting that? And how would you know if this would work? Now, for now, let's forget about the fact that a neural network usually runs on a GPU, so you would use WebGL, which means this is not really JavaScript. But you get the point. So to investigate this, to see how this really works, we should start with a simple problem and see if we are able to solve it. In the sense, are we able to know how much performance we can get out in this simple problem? And this simple problem is, of course, CPU bound, is find the first 25,000 prime numbers. It's just calculations. It's very simple. So the algorithm is something like for x that goes from 1 to, well, infinity. If x is not divisible by any member of an initial empty list of primes, then it is prime. So you add it there, and you go on until this list is 25,000 long. Then you know that you have found the answer. So that's it. And the question is, how fast will this be? Because we want to know the potential. And the problem is, how do I know? What should I expect? And so the idea is, we should experiment. Because to know something, you should try. And to experiment, that's a problem. We can write this in JavaScript, and we can even get the performance. But how do we know if this is good performance or not? There's just no way. So we have a contender, which is a JavaScript program. Now, don't bother about the code. This is code that does exactly that pseudocode that I showed before. And then we have another contender, which is a C++ program, which is almost exactly the same as the JavaScript one. If you just look at the shapes of the codes, they're just the same. I wrote them exactly the same. Which means, at least we have a baseline. So C++ should be fast. Now we know what will happen. So the idea is, let's race. So I have a script that does essentially everything. So I compile the C++ program. I run it. And I run it 3 times. And the answer is about like that. Now I execute the JavaScript one, and well, it takes longer. Let's say about 6,000, which means that the ratio between JavaScript and C++ is that one, so almost 4, which means that we did it, and now we know that C++ is almost 4 times faster than JavaScript. It's not so bad, right? What do you think about it? Are you happy? Are you sad? And I'd say, it is so bad. You deserve more. You shouldn't give up. You should demand faster. But how much faster? And could this be made 3 times faster? Who of you thinks it could be made 3 times faster? Nobody. So you're really pessimistic, which means, does some of you think that it can be made 30 times faster? 300 times faster? And again, how do we know? So we experimented. We know how fast C++ is, how fast JavaScript is, and how can we make sense of this? And the problem is that we need to be prepared. We need to know what to expect. We need to know how the virtual machine executes and optimizes code, and know how to inspect what's really going on. And you also need to know that we'll always get this wrong. You really need to experiment. In performance, there's just no other way. It doesn't matter how much experience you've got. The experience will put you, hopefully, on the right track from the beginning. Hopefully. And that's it. So now let's see how V8 optimizes JavaScript. This talk is V8-centric. I can assure you all the hints I will give you will work anyway across all the other VMs, because in the end, they are trying to do the same thing. I know V8 very well, so this talk is based on V8. So what is optimized code? Well, there are several steps on the road to optimization. The first thing you can have is an interpreter. An interpreter executes JavaScript, which means that for every JavaScript operation, there are lots of branches to select the operation and lots of machine code instructions. So something in the order of tens to hundreds of machine code instructions per JavaScript operation. Depends on the interpreter. Then you can have a fast JIT compiler. A JIT compiler that is fast, which means it generates machine code which calls slow generic operations. So again, it's not that much better than the interpreter. Then you can have a JIT compiler which tries to use type info. So it produces machine code to specific operations tailored at how this JavaScript is done. So this is getting better. And then you can have an optimizing JIT compiler, which is as above. So produces machine code, which uses specific operations, which means just a handful of machine code instructions per JavaScript operation, and looks at the big picture and does a huge amount of optimizations on the whole algorithm, things that compiler technology can do. Why don't we always do this? Because this takes time, which means this compiler takes a lot of time to run, and it runs while the application is running. So it's just not worth to optimize every single piece of code. You just optimize the important ones. So this is why all these things exist. They all have a place. Now, the first thing that is important to understand is a concept of hidden classes, which means that JavaScript has no type info in the source code, which means there is no way to do optimizations. But typed info can make code faster. Maybe like C++, how do we know? And so V8 internally creates hidden classes for objects at runtime. So the key point is that objects with the same hidden class can use the same optimized code. So let's look at a simple piece of code. We have a function, point. You give 2 coordinates, and it gives you x and y. So now you have this object that has 2 properties. And if we create one, P1, we have this object. It has an hidden class that says it has got x and y. Now we create another one, and it has the same hidden class. But if we say p2.z equals something, now this object has a different hidden class. And the idea is that a function will be fast as long as the objects are always shaped the same. Which means that now we are trying to avoiding speed traps. Why avoiding the speed trap? Because the idea is that if you're running fast and there is a speed trap, well, you need to slow down. Otherwise, you get a ticket. So the point is you are trying to avoid in speed trap. And in this sense, the idea is you should initialize all object members in constructor functions. And all of them are in the same order. And never touch the object afterwards. So the objects will always have the same shape. Now, there's another trick, fast numbers. Objects and numbers are very different, but in JavaScript, you can mix them freely. And V8, to distinguish them, uses tagging. So inside the virtual machine, there are values that are long like a register in the CPU. And these values could be integers or pointers to objects. And V8 uses one bit to tag them. And this bit means that values can be either objects or small integers or boxed double, floating point numbers that are larger. But the problem is that you should prefer, when you use integers, values that can be represented with 31 bits. So smaller than 2 billions or something, I mean, half a billion, that number. Because if you use integers with that size, which are fairly regular, then they will always fit in a small integer, and the VM will be able to keep them in the registers that it allocates, knowing that they work and so on. If your numbers grow from small to very large, and then the JIT will get confused. Because there's just no way. So if you know that the number will grow, will be a floating point 1, just use a floating point 1 immediately. It's enough to write plus the number in JavaScript, and the engine converts that to floating point. So if you do it, you know it, then the JIT knows this is a big number, then reserve a space from the start. Now, there is another performance hint about large and sparse arrays. We have arrays in JavaScript, and the virtual machine needs to manage them. And there are two ways to have an array in memory. One is called internally fast elements. That this array is really like an array in C languages. So it's a contiguous buffer of memory where you have all the elements. It's the linear storage, compact. And this has a very, very fast access. Otherwise, it can be in dictionary elements mode. It's a hash table storage. And let's see what happens here. We create an array, an empty one, and it starts empty. Now we have a simple loop, and in this loop, we iterate over the array, but we access the array element before having used that, allocated that in any way. This doesn't really work well. The piece of code below, you say you create the array, you actually initialize the element, and then you work on that. Now, this is silly code. I mean, it does nothing useful, but it's just to show the point. The second version is about 2 times faster, just because you pre-allocated that array element. So the JIT doesn't get confused. It knows what's going on. And even worse, if you delete array elements afterwards, then the JIT needs to leave holes, and then it needs to switch to dictionary mode, and dictionary mode is very, very slow. So if you think that an array is really an array, handle it as that. Otherwise, it's an hash table, and it's not really an array. So to avoid the speed trap, you should use contiguous arrays starting from the 0 index and going on. You shouldn't pre-allocate very large array, more than 64 key elements, because if you do, the JIT will say, you're kidding me. You are pretending you're going to use a huge amount of memory. I don't trust you. Usually people do this and they then don't use the memory. So the JIT will not allocate a huge buffer beforehand, which means this will go in dictionary mode. It's not good. And they don't delete elements in arrays, because if you do allocate the buffer and then try to introduce holes, the JIT says, oh, wow, there are holes. I cannot really use a buffer. This is not going to work. So it converts the whole array into a dictionary, which is expensive. So just know what you're doing and do it right from the start. And again, don't load uninitialized or deleted elements, because again, this is a bad thing. It doesn't work in a linear array. And there is another trick called specialized array elements. So this buffer of elements can have elements of different kinds. So if you have an array of numbers, and these numbers need to be large, the JIT can actually allocate an array of doubles, where each slot is large enough to keep a full double, floating point double. It does it, but it needs to understand that it has to do it. So in general, the hidden classes track the array element types and changes because of that. And unboxing causes class changes. So just don't mess with the types of the elements of the arrays. Look at this. So we have an empty array, and we use it properly from index 0 to index 3. But index 0 is a small number, integer, fine. Index 1, again, a number. So the JIT allocates a small amount of space, goes on writing. Then index 2 is a floating point. So the JIT thinks, oh crap, this was an array of numbers, but I cannot use small integers in the slots. I need to store doubles in the slot. So it reallocates the whole array to store doubles. Then in the third index, you store true. Well, true is not a number. It's actually like if it were an object. So the JIT says, oh crap, this array is not good. I need to throw it away, relocate a new one where each slot points to actually anything. It can be a small number or an object, which is a different thing. Which, if you do it like in the line below with a literal, then the JIT knows in advance. It can see all the types. So it can immediately do the right thing. So if you really, really want to use an array with mixed types, just use a literal. So the JIT knows and everything is okay. Usually you shouldn't use an array with different types. It really doesn't make sense in a proper program if you want to optimize. But if you really need it, do it like this. Which means initialize arrays using literal for small fixed-sized arrays, and actually pre-allocate small arrays to correct size before using them. This is something you can do. It needs not to be huge, but a small one is fine, which means the machine will not need to incrementally reallocate the array. So if it's something like 2,000 elements, it's still fine. Just allocate it and it will work. And don't mix non-numeric values with numbers. Again, this doesn't work. Doesn't work well. Now, about the JIT itself, does it need to be fast or optimizing? And historically, V8 had two engines. The full compiler, full gen, generated, let's say, good machine code for any JavaScript, and then the crankshaft produced great code for most JavaScript. Now it gained more engines and lost the previous ones. It's been fun because for a few years, it actually had all of them because it was transitioning. Now, what it has is Ignition, which is an interpreter for memory-constrained devices. It's important now that it is an interpreter because it starts fast. It doesn't need to compile. It interprets. So it's slower, but it's fast enough. Now we'll see how. And then it has Turbofan, which is a compiler which is incredibly optimizing. It's amazing what it does. The compilation pipeline is something like this. You start from source code. It gets parsed. You've got an AST, the tree that represents the code. And then there is a bytecode generator. And the bytecode generator can be interpreted by Ignition immediately. Or if this code needs to be optimized, it goes to Turbofan, which optimizes that and produces good machine code for any architecture. Now, Ignition is an interpreter that, as I said, starts executing code immediately. And it uses bytecode for this representation. And initially, it assumes nothing about types. So this will be slow. But there's a trick. There is the trick of inline caches. Inline caches, they have this name because in the previous compiler, they were stored inline in the code. And the code was self-modifying. So it was really inline. And essentially, they handle type efficiently. They have type-dependent code for every operation. So let's say you have to access an object element. The general way is I don't have a clue how this object is done. I invoke a function that looks at the object and tries to get the property out. Tons of machine instructions to do it. Now, if you know beforehand the shape of the object, the hidden class, then the proper operation is blatant, is fast. It's just address, offsets, get it. But you need to know it. So the idea is validate type assumptions first and then do work. So the first time you execute a piece of code, you call the slow one, but check the type and store it in the inline cache. Now, it's not inline anymore, the cache, but it's still called like this. And the next time, you validate the sham. Is still that type? Yes, I go the fast way. Did it change? Oh, I store the fact that it changes, so this is getting bad. And I go the slow way, because there's no other way. Which means that inline caches get better at runtime. And now the type information is used also by the optimizing compiler when it will be needed. So let's take this thing and just consider this dot primes. So just this piece of code, the property access. A dumb machine code stub is this, which for those that know machine code is a few instructions to create the stack frame and a call to a function. So this is low. Now, the optimal code stub is do a comparison of an object address to say if the hidden class is the one that I am expecting. And if it's not, well, jump somewhere else and go the slow path. Otherwise, do just this machine instruction. And this single machine instruction on an x86 architecture does the job of getting the property. So it's much better than before. But you need to have the type information to be able to do this. And now let's get to Turbofan, the real optimizing compiler. This kicks in when the code is hot. So there is an internal profiler. It says if a piece of code is executed a lot of times and has enough type info, then it uses type info and optimizes really, like there's no tomorrow. This is the Turbofan pipeline. Now it starts here. It can start either from the AST or from the bytecode, and it produces graphs. So a representation of the code that is a graph with all the dependencies of every instruction. Then there is a pass of inlining and lowering. You have a simplified graph. And on this simplified graph, you do optimizations, all the kind of optimizations that a native code compiler can do, a really advanced one. And then you have a machine graph, which is a graph of instructions that look like machine code instructions. At this point, it's again compiler pipeline technology, the scheduler, and then the backend, and then the machine code. There are a few nice things here. If you are starting from WebAssembly, WebAssembly actually already describes things that look like machine instructions. So you skip all of this portion of the pipeline. You already have something that looks like machine code. You already go here. Because the optimizations have already been performed by the compiler that compiled like mscripten, something like C or C++ into WebAssembly. It already did the optimizations. There's no point redoing them. You just do the more specific one with the scheduler, machine-dependent ones, and then we go on. And now there is this thing. This piece of the pipeline, in my opinion, is a gem. So the V8 engineers had a problem. They needed to build an interpreter. They didn't have an interpreter before. And the interpreter needs to manipulate JavaScript values in a way that is compatible with the JIT. So writing the interpreter code is very hard because it needs to be efficient, and the format of the data needs to be exactly the same as the one used by the JIT. So this machine code of the interpreter needs to be very similar to the one that the JIT uses, but you usually write the interpreter in C++. So they solved the problem, essentially writing the interpreter so that the interpreter uses stubs, pieces of machine code, that are actually generated by Turbofan. So they invoke Turbofan to say, okay, give me the stub of machine code to do a property access. Give me the stub of machine code to do a multiplication, and so on. So they build all the stubs for every elementary operation, and they are built by Turbofan, so they are compatible with Turbofan. And the interpreter actually calls those stubs, which is funny. So you have the code stub assembler that essentially goes inside Turbofan. In my opinion, this is a gem. It's an implementation thing that is, okay, it's not really interesting for JavaScript developers, but I love it. Now, megamorphic tag, what does it mean? It means that inline caches start without initialization, and they are monomorphic. So they say this thing has this type. But if a different type is used in that operation, then they get polymorphic. And then the JIT can still cope with that sometimes. But if it changes type too many times, then it gets megamorphic, and they say, I don't care, I don't know. I have no clue what will happen here. I will always call the slow operation, and which is bad. So think about this. There is a function, which is add. You pass x and y, and you return x plus y. You invoke it like this, and then it's monomorphic. You invoke it like this, and it becomes polymorphic. Now, the virtual machine here, inside the code of add, for the plus operation, will say, what should I do? Should I call the integer add or the string concatenation? No way. So it will need to be slow. It will need to check and see. This is what polymorphic means, which is bad. which means avoid the speed trap, prefer monomorphic over polymorphic. Now I will gloss over this. It's funny. In Redux, there was a funny issue because essentially Redux and React were causing polymorphic code, and the V8 engineers tried to track that. It could be fun to look at that, but it will take too much time. So about the optimizing compiler, I already said this. This reoptimizes hot functions, and type information makes it faster. And operations are also inlined speculatively, so they will get even faster. And monomorphic calls are inlined. And inlining enables more optimizations because you have visibility of the code, so you can move pieces of code here and there. It gets even better. And this is, okay, maybe a bit unreadable, but this is the whole sequence. Access the property, access the index, get inside, take it out, and do the modulus. And this is just this handful of machine instructions, which is something like, is this a prime object? Otherwise, go away. Fetch the property, just one machine instruction. Test if it is a small integer. Test if the array is of the correct kind. Take the array length, check the array bound, load the element, convert into integer, do the modulus. One machine instruction per operation apart the checks. It's hard to get faster than this. And good news, no more bailouts, which means in the past, some constructs could not be optimized, like try-catch. I've been personally involved in this. And now Turbofan optimizes everything. So this is good news. But there is the ghost of the optimization, which means that the optimizations are speculative. Usually, they pay off, but if something bad happens, so if a type changes, you have the optimization. And the optimization needs to throw away the optimized code and resume execution at the right point in the interpreter. This takes tons of time because you have a context which is in the optimized code with values in registers, in memory and everything, and you need to switch execution to a totally different context which should represent the same context, but in a totally different form. So, and then you throw away the optimized code. So, eventually, the code will be optimized again with the new type information, but for now, things slow down, which means that you should really avoid hidden class changes. This is probably the most important thing of all. And the fun thing is that even if indirectly, using typing like flow type and TypeScript can help, because if you write strongly typed code from the beginning, the type of things is that one. It's the thing that TypeScript or flow type are saying, which means that, oddly enough, using those things also help performance, but really indirectly. So now we know the tools. We know that we can use the profiler, and we can log what gets optimized with tracing. We can detect optimizations with other command line options, and we can pass these options also to V8. So this is something that can be done in the browser. And which means now, are you prepared? You should ensure that the problem is JavaScript, which means it needs to be pure JavaScript, no DOM, no network access, no anything. I'm talking about JavaScript, not other things. You should collect metrics, so measure speed, profile, locate the bottlenecks, and once you know that a particular piece of code is the bottleneck and you think it could be faster, you should fix the problems. So let's make it faster. Let's do it. Now here, to fix the thing, recap, this was the ratio of performance between C++ and JavaScript. Now we get the profile data, now it's pre-computed. And if you look at the profile data, we see something very strange. If you look here, essentially, a lot of ticks are spent in the lazy compile, but an incredible number of ticks are spent in the modulus operation, in calling a function that accesses the modulus. This is plain wrong. So you should look at really what happens under the optimizations, and if you go down and see the call stack, you again see that this was called by fmod in the modulo and so on. Then, now I make it shorter. If you look at the code, you will notice that I did something silly. Here, there was, in the loop, less than or equal to the count. So actually, this was going past the last element of the array. It was harmless from the semantics. You didn't notice. It was still correct. But now that you know what was going on, you really see. So it tried to actually do the operation, but the operation failed because the element wasn't there. Now with just this correction, so this is the output of a diff, the code is like this, which means what? I got lost in the code, sorry. Okay, so now here with this, we see that this is the proper operator. And now let's run it again, and we see quite a different time. Okay, now the benchmarks are what you mean. So let's say that the value is this, and the proper profile data now is proper. So if you look at the ticks, everything, so really everything, is in the main, which is the function that should do it. We don't have that time in C++ code anymore, which means that the JIT is working properly. And now we run the C thing, and crap. What happened? The ratio is this. So is JavaScript faster than C++? It goes 3 times faster, but what does it mean? The problem is that C++ was not optimized. Now, we optimize the C++ code, and we run it, and now we get this time. Now, Enscripten to the rescue. So with this time, we say JavaScript is 45% slower, which is not bad. This is OK. But let's try to compile the C++ code with Enscripten and run it. And, well, we expected it to be faster, but we forgot one thing. We didn't optimize it. Now let's compile it again, optimizing it. You see this thing. It says optimize the code. Now let's run it. OK. Now it's getting better. So now we are really there. Now, the funny thing is, I just tried to introduce type information there, and we see that it got 10% faster. This was a modification I did to the JavaScript. We can fix the algorithm. And if we fix the algorithm, I'm going a bit fast because I see I'm being a bit slow. Fixing the algorithm means we are choosing a different algorithm. We are essentially noticing that we can stop at the square root of the length of the array because a number that is the square of the other cannot be bigger than the prime. So it's a mathematical thing. And if we do this, it takes like this. So it's a 30 times speed up. What does it mean? Well, essentially, this means that if you picking the right algorithm is more important than fine-tuning the optimization. Just this. So we got it 30 times faster by picking a better algorithm. We just got it something like a few % faster by adding the type information. So the most important thing is design properly. Then if there really is a performance bottleneck, know all these things and apply them. Now, another example, we still have a bit of time. Perfect. I did a small program which essentially simulates something like a grid of nodes connected to each other. So the grid is a matrix, which is an array of arrays. And inside this grid, we have the possibility of getting cells, which means we are just accessing the matrix. And then what we do is to connect the cells to the neighborhood ones. So we set references to all the neighborhood ones. This is just to test something that looks like a grid, could look like a computational intensive thing. And this code, if I execute it, I get something like this. Okay, so 4 seconds something. If I build the arrays properly, so this is the diff. The diff is just allocate the arrays with the proper size right from the beginning. I run it, and I get this. So just that modification, you see the speed up. Now, with this modification, which is I initialize the property beforehand, like I was explaining before, I run it, and I get this. Which means we double the speed with 2 silly code modifications. Now, I said, OK, let's build this in C++. Now, here I didn't cheat. I wrote the C++ program like a C++ program should be written, allocating all the memory in a single big buffer, using pointers, using all the tricks of the trade. I compile it, optimize it, I run it. Now, this is fast. There's no comparison. So I said, OK, let's use mscripton, and let's run it. OK, now you get the point. Which means, if you write JavaScript normally, you can get very near to C++ speed for certain problems. For others, it's difficult because the language is different. At that point, go WebAssembly. But only at that point. Because for normal code, I mean, it's close enough to C++ to be OK. And that's all. I don't know if there's really time for questions, but, well.
Pure se ci sono domande, vi passo il microfono.
Perfetto. So, questions, anyone? Was it too much? Oh, there's one over there. Just in the farthest place possible. The microphone will get there eventually.
Dove?
Hi. Is there a way to see the actual compiled code, like the assembler code of the...
I cannot hear the question.
Okay.
Sorry.
Is there a way...
OK, repeat the question, please. Sorry.
OK. Is there a way to see the actual assembler code generated by all these steps,
yes.
the subsequent step?
Yes, there is.
Yeah.
Essentially, there are, again, options that you can pass to V8 to dump the code generated by the compiler. And again, these options can be passed to Chrome. So if you start Chrome with these options, then it will log everything just to stood out, but well, it's OK.
OK, so you can see all the steps and the code getting optimized by all the subsequent steps.
I generally prefer doing these things with Node, because it's just more comfortable. So if you can extract your piece of JavaScript and run it inside Node, it's just simpler, less cumbersome. But you can even do that in Chrome.
OK, thank you.
Right.